Hello, welcome back. So today we will be talking about one of the most fundamental and maybe central topics in both system dynamics and controls is the topic of stability. Um, so I'm not going into many of the actual theoretical definitions and theoretical proofs regarding stability, but for now I think it is enough to provide the basic concept of what we call, what we mean when we say a system is stable or unstable, and how it relates to what we have talked about so far. So there are a few different definitions of stability. One of them that is more general and useful is what is called a Lyapunov stability. Lyapunov stability, or stability in the sense of Lyapunov. Again, this is not a formal definition, but the essence of it is that imagine you have a system and you initiate your system at a point. So this is the initial condition, and your system is called, and your system goes about and shows different behavior. The system is stable in the sense of Lyapunov when you can define a point and a sphere around it, such that when you initiate your system within this region, the response never leaves that region. So this is called stability in the sense of Lyapunov, or sometimes Lyapunov stability. And we'll be using this and another definition a bit later about the input-output relationship of the system. So let's see how we can relate this concept to what we have so far. To begin, let's start with a very simple condition, or simple example. X dot plus AX equals 0. A first order linear system with a constant A. For now, let's assume no input. So the response to the system is something of the form e to the minus at. Depending on initial condition, it could have a little bit other stuff, but for instance, a constant before that, before the term. But this is the very general form of the response. Now I can consider two conditions. If my A is positive, so what I have is then some e to the minus power or negative power, and as time goes to infinity, my response looks like this. So this is time, this is x. So this fits the idea that whenever I initiate my response from somewhere, I can always define a bound such that my response never leaves that bound. So my bound in this case would be two-sided, plus and minus that value. Conversely, if my A is negative, then my response is going to look like this. And doesn't matter how big I can try to have this window or region, my response will at some point leave that region. So these are the hints that when my constant A is positive, I have stable. I have stable behavior, and if it's negative, I have unstable behavior. So this is just a single case, maybe to try to relate it to the ideas of transfer function. What is the transfer function of this system? I have S, x of S, plus AX equals 0. So if I write my x of S is 1 over S plus A. And really what the value of A that we were talking about is essentially the pole of this system. So my pole here is minus A. So if my pole is negative, I have a stable system. If my pole is positive, I have an unstable system. So this is interesting, that this is a good hint where we are getting at, that the poles of the system kind of show me whether the system is stable or unstable. To further work this concept, maybe a couple of reminders that whenever we have a linear time invariant system described by a complex differential equation, I have, let's write it. Reminder 1, in a linear time invariant system, the response is a combination of some e to the negative or e to something t. And what was inside was a pole of the system. So if all of the poles are negative, I could have this multiplied by some sine and cosine, some oscillatory functions. So maybe sine. So if all of these terms have this e to the minus something t, means that my signal eventually comes down to 0 within an envelope. So that's that. And the second reminder, maybe to be more explicit, the power in e to this minus something t how do I write it? This is, let me put it this way. The power, what I have is usually e to the minus some sigma t, and this sigma multiplied by something else. Sigma is the real part of the pole. So my poles are usually p equal some sigma plus j omega, or plus minus j omega, depending on whether it's could be purely a real system when sigma is real and omega is 0, or if I have a complex pair, I would have sine and cosine of some omega t in there. So with these two reminder, we can really think of it this way. So if this is the S-plane, and I find all my poles and show it on this plane, as long as my poles have negative real parts, so all these sigmas are negative, I have a stable system. Otherwise, even if one of them, even if a single pole is on the right hand plane, it has a positive real part, that single exponential will make the system unstable. In that case, you won't be able to find these bounds that the response stays within that region. So if I find all my poles, if any of them is on the left, on the right hand plane, I'll have unstable system unstable system. Conversely, if all my poles, and I emphasize on the all, are on the right hand or left hand plane, I have a stable system. So this is the beginning, the starting point that we can look at the poles of the system and infer whether the system is stable or unstable. Maybe I can, before erasing, I can add a few comments here. So the first comment is, stability is defined for a system. Stability defined for a system, and by that I mean it is independent of the input. What are the inputs to the system? It is essentially a natural response of the system. So if you give it some initial condition, does your system blow up, or your system goes and converges to a single value? And that brings me to the second comment. In linear systems or linear time invariant systems, we always have something called asymptotic stability, and by that we mean response goes to 0. Not only it stays within a bounded region, it always goes to 0. So that is the case for linear time invariant system. And this actually would not be the case for nonlinear systems. Nonlinear systems, in terms of stability, they are quite interesting. Anyways, again, going back to the topic, stability is defined for a system. It is also, in this sense, defined for a single point. Whether a point, this point that we are looking at its vicinity, whether that point is stable or not. But again, this doesn't apply for linear system. Well, this distinction doesn't apply because that point for linear system is always 0, and the system, we don't need to worry about any other point, the stability of other points outside just 0. And the last comment. So we said if A is positive, A is negative. Same here. Positive real part, negative real part. Let me write it down here. If all poles have negative real part, we have a stable. If a single pole has positive real part, we have unstable. Okay, this is good to have. So what about poles that are neither positive or negative? They lie on the imaginary axis. So before talking about what they are called, so if I only, sigma is 0 and I only have some j omega, my response will look like a sinusoid. So in this case, it is never going to 0, but it's also not unstable. So in this case, what we have is something called marginal stability. Marginal stability. That is somewhere in between a stable and unstable. So this is when when I have 0 real part of poles. So again, if any of the poles lie on the imaginary axis, the real part is 0, that single one will continue to oscillate forever, although the rest of the poles or rest of the modes of the response will convert to 0. That single one will continue to oscillate, and I will have marginal stability. So, well, maybe now that I'm here, one last bit as a visualization. I think it is helpful. Let's do it here. So this is my S-plane again, real and imaginary axis. And let's look at what happens to the response if I have poles in different regions. So if my pole is here, just a single pole on the real axis, but it is positive. So in this case, my response will look like this. If my poles are, again, on the right-hand plane, I have positive real parts, but there is this complex pair. So in this case, this combination of poles will lead to responses that look like this. So it will exponentially blow up. If I have poles on the imaginary axis, my response will be a non-ending sinusoid. If I have poles with negative real part, but again outside the real axis, I will have oscillations, but my oscillation will die out So this is how the response will look like. And maybe last thing, if I have a pole on the real axis but negative side, without oscillation, my response will go to 0. So now this has become too dense. So let me clean up the board before we leave. So this is all response due to the initial condition. So this kind of stability is very easily and useful defined for a system as a whole. And when we do not have input. So let's clean up the board, talk about a slightly different definition of stability that takes into account input, and see how these two are related. Okay, the other definition of stability, let's take a quick look. When the system has inputs, we can look at the input-output relationship and define another form of stability called bounded input, bounded output, or simply BIBO stability. So here, by bounded input, I mean the size of the response is always smaller than some constant value. So you can always find a value that your entire signal is less than that. So this bounded input, bounded output stability is useful when we are dealing with input-output relationship. Taking it without the proof, the necessary and sufficient condition of a system being BIBO stable is that necessary and sufficient condition of BIBO stability is that the impulse response is what is called integrable. So mathematically speaking, this means the integral of 0 to infinity of y delta of t dt. This one exists, well, it's not infinity. What this really means is that the transient response dies out. Dies out. So if I strike my system with a hammer, it does something, and the response eventually should go to 0. So if this transient response due to impulse goes to 0 and this integral exists, then your system is BIBO stable. So this is the kind of formal definition, but let's see how we can break this into something slightly more useful and manageable. So remember that the response of y delta of t is essentially the Laplace inverse of g of s, my transfer function, times the Laplace of input, which in this case, because my input is an impulse, this is 0. So really what we need to look at is this transfer function. So the system is bounded input, bounded output is stable only if my transfer function behaves a certain way, and that can be and that argument can then be generalized to any arbitrary but bounded input. And to do this, again, the same exact pole analysis. So if we look at the poles of transfer function g of s, if my poles have negative real part, I have a stable system. And again, even if a single pole of the transfer function, if any pole has positive real part, I have unstable. Stable and unstable in the sense of bounded input, bounded output stability. And one thing to remember here is that the kind of the middle ground, what we call marginal stability, in this case it is unstable BIBO. So if my poles are on the imaginary axis, if I strike my system with a hammer, the system will start to oscillate forever, and this integral would not exist. So that means this, if a system is marginally stable, it is unstable in the sense of bounded input, bounded output stability. Okay, so this is another definition of stability, and you can see for linear systems, these two, the stability in the sense of Lyapunov that we discussed just before I erased the board, and this bounded input, bounded output stability, they are almost equivalent in the sense that if you look at the poles of either your transfer function or your dynamics in general, which are the same thing, your system is stable if the poles have negative real parts and unstable if they have positive real parts. Okay, so these are the definitions. Let's look at one tangible example to see whether we can make sense of these definitions. Again, going back to our usual mass spring damper system, and I'm going to give it some input P, and let's analyze the stability of this system. Let's look at the bounded input, bounded output stability. So the transfer function of this system, which is, let's call this x of s over p of s. This transfer function is 1 over ms squared plus bs plus k, and this was k, this was b. So that is my transfer function, and even if I neglect p and look at only the response due to initial conditions, remember that it is exactly the same thing. Possibly I have some terms up here that depends on the initial condition, but the poles that defines the denominator, the characteristic equation, that defines the modes of the system, modes of the response, remains the same, whether we look at the transfer function or just the dynamics of the system on its own. So the two poles, the characteristic equation, is this one, or characteristic polynomial sometimes is referred to, ms squared plus bs plus k equals 0. And the roots of this are my poles. So my poles, P, or I had P, let's call it poles, equal just the roots of this quadratic equation. So it's minus b plus minus the square root of b squared minus 4mk divided by 2m. So these are the poles. And now let's see what happens if I have different values of parameters. Whether the system is stable, unstable, and under what conditions things may switch. So one thing to notice is that I have a minus b divided by 2m plus minus some term under the square root. So if my m and k, let's go here, if m and k are positive, so what I have is b squared minus some positive value. So in this case, b squared minus 4mk is always less than b squared, which means the square root is less than that. This one is b, so I'm taking minus b. The worst case scenario is if I have this plus, but it is going to be added to a smaller value. So all of this will have negative real parts, regardless of the parameter and values of the parameters. If all my mass, spring stiffness, and damping are all positive, meaning that they are physically meaningful components, this mass spring damper system will always be stable. So minus b plus minus square root of b squared minus 4mk over 2m. The real part of this is always negative. I'm going to put this because there is a possibility that when b is 0, I'll have minus 4mk and 0 real part. So this one is going to be just some plus minus some j omega when b is 0. My poles are going to be just plus minus j omega, and in that case I'll have only an oscillation, which makes sense as we know there is no damping, no energy dissipation, so oscillation continues forever. So if I want to summarize this, the system is always stable given that I have positive mass, positive spring stiffness, and positive damping. My system, regardless of what it is, remains stable. So I might have poles that are complex conjugate, We saw it before. The system response looks like this. Well, it's not a good damped oscillation. Let me plot it better. Something like this. That's better. Or I might have two poles like that, which the corresponding behavior of those two poles will look like this. Or sometimes I might have two poles on the imaginary axis, and for these the system is marginally stable or unstable in the sense of BIBO stability. Okay, so that's all for here. Let me clean up the board. A couple of more cases and examples, and we should be done with this topic of stability. So as a last example for this topic, let's first of all combine the idea of block diagrams and transfer function and all of that with stability, and look at the stability of feedback systems. So I have a very basic feedback system. I have the plant G and let's call it gain H. And for now, a few assumptions. First of all, this is a positive feedback loop. So the output of this summation is X plus H. So that's one thing to have in mind. Also, for simplicity, let's for now assume my feedback is just a constant, 1. And my system is something we call integrator. It has a transfer function of 1 over S. And maybe you already know this, or if you don't, why we call this integrator. So imagine I have some input U, and multiply by this G of S. This G gives me my Y. And this G is U over S. Yeah, I didn't write it. Well, it's good enough. So U times G is 1 over S, so I have U over S. So from here, YS equals U. This is the Laplace transform of the differential equation y dot equals U of t. So these are should be U of S. Y dot equals U, or Y equals integral of U dt. So that's why 1 over S, we call it an integrator, because it is very, in a sense, is being an integral of whatever the input is. Okay, anyways, before moving on, just the integrator itself, when I have G of S, G equals 1 over S, the pole of it is P equals 0, the pole. So the integrator itself is a marginally stable system, and maybe it is useful to have that in mind. So let me write it down. G is marginally stable. Okay, with the assumption that my feedback is positive. So this signal, let's call it, I don't know, some X, let's call it Z. I don't want to call it E because it doesn't make much sense here. So Z is this X plus output of H, which is Y times H. So I have Y H plus X, and the output then y becomes gz. Oops. Gz, which is g times yh plus x. And rearranging things, what do I have? Y times 1 minus gh equals gx. So the transfer function of the whole system, y over x equals g over 1 minus gh. So now the system, let's call it, no, keep it as is. So for the system that h is 1, g is 1 over s, this one is 1 over s divided by 1 minus 1 over s. So g times h is still 1 over s. And if I simplify this, it's going to be s minus 1 over s divided by 1 minus, or s minus 1, s minus 1 over s, and canceling the two s's from top and bottom, I have 1 over s minus 1. And the characteristic polynomial is s minus 1. Solving that equals 0, so the pole is p equal 1 plus 1. So it has a positive real, it is positive, t positive, which means the system with this positive feedback loop is unstable. So let's take a moment and see what this means. So G, we said, is an integrator. So whatever input comes in, it starts to integrate that and gives us output Y. So this is a complete feed through, so H is 1. And what is really happening, given some X input, my system starts integrating and then adding up, it essentially piling on its own output and keep increasing and increasing every time we go over this loop. We add to the value of the output, and that's why the system has this exponential increase or exponential growth. And it is evident by the pole of the system turning out to be plus 1. So let me do a few modifications. Maybe I should have done it earlier. Which one is better to do first? Let me make this, instead of 1, let's make it equal to k. I'm going to write it with blue. So let's call this k. Is it different? It is not. Is it? Not really. No. Blue and green looks green. Indistinguishable on the camera. Okay, let's do yellow. Let's see if yellow is different than green. No, all of them look the same. Red is my last resort. Let's call this K. Finally, something that looks slightly different. So here, H, this one becomes K. and this one was K, this one becomes K, and this one becomes K, and this one becomes K. So if I increase my gain, my positive gain in this case, I'm just shifting my pole further and further to the positive side, and that makes it a stronger positive feedback, and the response grows faster than when it was 1. Another thing I can change or keep track of is this positive. If I change it to negative, so let's see where that goes. This one becomes negative. I add a negative here. This one becomes negative. So this one becomes positive. That one becomes positive. And this 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 one becomes negative. So if I change my feedback loop to a negative feedback loop, now Z is the difference of this reference X and the output of my feedback gain. Following this through, I'll end up with a negative pole, meaning that the system is now stable. Now going back to here. So my system was kind of in between, neither stable nor unstable. Adding a positive loop and increasing the gain of that positive gain made my system more and more unstable. And conversely, if I created a negative feedback loop, my originally marginally stable system now becomes stable. So this is an example of when we have a system whose original stability condition is not what we want, we can adjust the stability and potentially make the system stable by using feedback gains. So maybe I can take this a little further. Let's see if my last color, orange, I think this one will look the same as red, but let's pretend now my original system is unstable. So A is positive. So this one now originally had the pole of S equal A, and if my A is positive, the system would be, my G would be unstable at the beginning. So let's see if I track this everything. Up to here, nothing changes. This one becomes S minus A. And this one goes here. If I do this, I'll have a minus A here. So I have S plus K minus A, that is plus. This is S plus K minus A. And my pole will be minus K plus A. So remember, A is positive. So if my feedback gain is large enough, its magnitude is bigger than A, it is now possible to essentially shift my pole from the positive side back to negative side and make this originally unstable system stable. So if I want to draw this, originally I had my pole here at some positive A, and through feedback I brought it back to some value minus K plus A. And by this kind of shifting or changing the position of the pole, I made my entire system stable. All right. So that was another example. I don't need this. So maybe the last comment, let's slightly talk about the position of the poles and what they do. Again, this is my S-plane. This is real and imaginary axis. So let's look at two conditions, maybe three. If I have poles here, my response looks like an undamped oscillation. If my poles are here, so I'm going to plot this here. Because I have negative real parts, I have that exponential term that pushes everything to zero. So I have, again, that's not a good damped oscillation. I should practice this more. So starting from here, okay, that's perfect. If I shift my poles further back, what happens is, so all of these have the same well, it doesn't really show, but they all have the same imaginary values, but the real part is just moving. So my oscillation should have the same frequency, but it's a matter of how fast the system is damping. So how do I do this? No, again, not the best. So what I want to plot is an oscillation that damps out faster. It's the same frequency, but it is brought to zero faster. So it's going to be something like that. Again, not great, but all three of them have the same frequency of oscillations. But as I shift my poles further back away from the imaginary axis, essentially I make my system more stable. That's not a very good and accurate term, but by more stable, I mean the system converges to zero faster. And same situation is on the other side. If it's positive, if the poles are positive, I have more instability if my exponent diverges faster when the poles go further to the right. Okay, and maybe last point that I can say it with words without writing it down. So if a system is stable, either in BIBO stability or Lyapunov stability, the important part is that the initial condition, that the response due to initial condition, the natural response of the system, will eventually die out, and what is left of the system is going to be purely based on the input, and the input drive the output signal without any lingering effects of the initial conditions. So that is all I have for the topic of stability. And you can see with the ideas of transfer function and a little bit before the general equations or the dynamics of the system, we can define and analyze whether a system is stable or unstable. And this is very useful, especially when we talk about designing control systems, that often we want to either make the system more stable than what it is, or make an unstable stable using control. Okay, with that, I leave you with these topics and see you next time.